Next up, we have oral presentation 15, Stamford, Connecticut, Team 1, Mission 12 finalist proposal.
Hello everyone, we are one of 3 finalists from Stamford High School in Stamford, Connecticut. Our names are James Pease,
MTS Uden,
Vedant Ganu,
Jordan Ordonez,
and Augustus Dorico.
and we will be presenting the efficacy of acetazolamide on carbonic anhydrase in microgravity. Our exploration of space has encountered another unanticipated hurdle, vision impairment. And as Lori Provin from CASIS mentioned before, astronauts' eyesights are going crazy. According to medical flight tests conducted by NASA, about 50% of long-duration ISS crew members have reported subjective degradation in vision, primarily an increase in farsightedness. So while astronauts are coming back to Earth with their distant vision intact for the most part, their near vision acuity is decreasing for the worse. This deterioration can be related to papilledema or optic disc swelling, which is another thing that astronauts suffer with on the ISS as a result of increased intracranial pressure. NASA has coined this phenomenon VIIP, or Vision Impairment and Intracranial Pressure Syndrome. So when looking to the solution for this eyesight dilemma, we took the lead provided to us by NASA, increased intracranial pressure. So we ask ourselves the question, what gives rise to this increased intracranial pressure and why?
Well, the source of this pressure can be linked to a fluid known as cerebrospinal fluid, or just CSF for short. CSF is a bodily fluid which provides cushioning support for our brain tissue. CSF normally flows through the ventricular system in our brain and then out of the cranium via the arachnoid granulations and then down the spinal cord. However, in the microgravity conditions that our astronauts face, CSF builds up in our brain and damages our eyes. So this leads us to our next question. How can the pressure be reduced? So, as we said before, there's too much CSF being built up in our brains. So if we reduce the amount of CSF, then we reduce the amount of pressure accumulation in our brain. So we look to the production of CSF. It happens in each ventricle, which has a choroid plexus structure comprised of specialized cuboidal epithelial cells, which allows for ion migration across it. It acts as a membrane so that ions can flow to one side of the cells and then create an osmotic gradient to pull water across and create the fluid. So, as if we reduce one of these ions that are being pushed to one side, then we reduce the amount of CSF being created as a whole, and we somehow cure the eyesight degradation.
All right, so one of the integral components of CSF that we found is bicarbonate. And so where does bicarbonate come from? Bicarbonate is an ion. So where does bicarbonate come from? So it comes from the dissociation of carbonic acid into H+ protons and bicarbonate ions. And carbonic acid is already located in our blood, but the enzyme that actually catalyzes the reaction to create more carbonic acid is called carbonic anhydrase. And so the logic that we're following here is that if we reduce the catalytic effects of carbonic anhydrase, then we can reduce the amount of bicarbonate formed and eventually CSF. So the inhibitor that we chose to go with is called acetazolamide, also known as Diamox in the marketplace. And we went with acetazolamide because it's more known. Doctors have been using it for papilledema on Earth and for many other cases.
Now onto the way that our experiment is set up. Our two will be split up into 3 different chambers, one holding 3.2 milliliters of gelatin, another 3 milliliters of acetazolamide, and the last one 1 milliliter of blood. On the first day, we will release a clamp that separates the solutions of acetazolamide and blood, allowing for them to mix together thoroughly. And 2 days later, we will release a clamp introducing the solution of gelatin. Then, gelatin will take form effectively in order to preserve our results from the experiment. Then it will undergo a 50 degrees Celsius water bath to melt down the gelatin, and then a 35 degrees Celsius water bath to temper it down. We will then measure the pH of the solution, and we ask ourselves, why is this important?
So it is important and relevant that we measure the pH of the blood, and we have the following rationale to explain why it is important. There's an exponential relationship, would you take this? There's an exponential relationship between hydronium molarity and pH of a substance. So if we measure the pH, we will know the hydronium molarity. So Since bicarbonate and hydronium are produced at a 1-to-1 ratio by the dissociation of carbonic acid, we will implicitly be measuring the bicarbonate molarity via pH. Once we've obtained the pHs of the respective samples, both experimental and ground truth, we'll be able to make a conclusion as to whether or not the acetazolamide was as effective in microgravity conditions as it would be on Earth. Should there be a difference between the efficacy of acetazolamide in microgravity conditions, the scientific community, or perhaps even ourselves, will be able to make a determination as to what a sufficient dosage would be for our astronauts in order to impede the vision impairment they're undergoing. So firstly, we would like to give a special thank you to the Toshiba America Foundation, who's provided us with a grant with which we have bought a rotating wall vessel to simulate microgravity so that we can continue our research in spite of not going to the ISS. And we would like to thank all other organizations involved. And finally, we would like to thank Ms. Sue Dougherty for being an exceptional teacher facilitator in this great program of ours. So thank you.
Do we have any questions?
So I'm Caleb from Fitchburg, Massachusetts. And if you said this was same process was be using as a prescription drug now, is there any side effects that are involved with that our astronauts would have to face from this method?
Thank you, Caleb. So the side effects that we've seen on Earth consist of a lack of lubrication on the spinal cord. CSF acts as a cushion, as we said previously, and lubricant. So without that, with the decrease in CSF, we might have astronauts with sore backs, but I think that's preferable compared to vision loss and blindness.
Thank you.